November 10th, 2025. Just before dawn over the Karoo Desert in South Africa, something happened that will reshape the way we listen to the cosmos. A signal was captured. Not noise, not interference, but a structured chemical fingerprint. The object responsible, 3I Atlas, the third known interstellar visitor to pass through our solar system. But this one did something the others never did. It spoke. No, not in words, not in pulses or code, but in chemistry. A message written in the ancient language of water splitting apart under starlight. And that message? It came from nearly the same region of space as the infamous WOW signal from 1977. In tonight's quiet deep dive, we're going to walk through the facts, the chemistry, the data, the geometry that made this detection possible, and the anomalies that continue to confuse astronomers. If you're listening right now, drop a comment with where you're tuning in from and what time it is there. Let's explore what it means when the universe speaks, and what exactly it's trying to say. Until very recently, our understanding of interstellar objects was built on a foundation of silence. The first time humanity confirmed the arrival of a visitor from beyond our solar system was in 2017. That object, now known as 1I Oumuamua, caught astronomers by surprise. It was small, elongated, tumbling chaotically through space. It entered on a hyperbolic trajectory, meaning it wasn't bound to the gravity of the Sun. It came in fast, slingshotted around the inner planets, and then disappeared. What made Oumuamua even more puzzling was how it moved. It experienced a strange acceleration as it left the solar system, one that didn't match the usual gravitational forces. And yet, despite the excitement, despite countless telescopes tracking its path, it remained completely silent in the radio spectrum, no signal, no emissions, nothing that could be interpreted as communication or even radioactive chemistry. 2 years later, another visitor appeared. 2I Borisov, discovered in 2019, was different. It looked and behaved much more like a traditional comet, with a visible tail, a coma of gas, and predictable outgassing behavior as it approached the Sun. But like its predecessor, Borisov remained mute to our radio telescopes. No detection of molecular signatures, no absorption or emission lines, no hydroxyl, no chemistry speaking through the electromagnetic spectrum. If interstellar comets were a thing, it seemed, they would be optically active but radio quiet. This consistent silence formed a pattern. Scientists began to treat it as an expectation. Interstellar objects, by their nature, move quickly. They often have steep trajectories and spend only brief windows of time within observational reach. They're dim, difficult to track, and generally not energetic enough, or long-lived enough, in our system to warrant large-scale radio observation campaigns. Optical and infrared telescopes were our go-to tools. Radio instruments, it was assumed, wouldn't hear anything even if they tried. In fact, some astronomers believed that radio detection of interstellar visitors was simply outside the realm of possibility. The thinking was that, unlike comets native to our system, these objects hadn't evolved in proximity to the Sun. Their chemistry might be frozen, their volatiles trapped beneath thick layers of dust, or their structure too compact to allow meaningful outgassing during their quick passages. Add to that the chaotic motion and uncertain rotational behavior of these bodies, and you had a recipe for radio silence. This silence wasn't discouraging, it was expected. Even the most sensitive instruments like ALMA or the VLA, Very Large Array, failed to detect anything conclusive from earlier interstellar visitors. So when 3I Atlas was discovered in 2025, there was excitement. Yes, but cautious excitement. Nobody expected a breakthrough in radio frequencies. No one anticipated what came next. Radio observatories around the world kept an eye on 3I Atlas, but mostly as a formality. The real work, many thought, would be done by optical observatories like Hubble or space-based infrared platforms like the James Webb Space Telescope. Spectrographs would analyze reflected sunlight, study tail dynamics, and map chemical ratios through ultraviolet light. But in radio, it was treated as background noise, routine monitoring, with no reason to expect surprises. That silence, that expectation of silence, is what makes the discovery on October 24, 2025, so remarkable. Because on that day, the MeerKAT array in South Africa didn't hear nothing. It heard chemistry. It heard water breaking apart in real time, and for the first time in human history, an interstellar object had spoken, not in symbols or pulses, but in molecular structure. The age of silent visitors was over, and 3us Atlas had just rewritten the playbook. It began like most observation sessions, quietly, methodically, without ceremony. In the early hours of October 24th, 2025, as most of South Africa still slept, the MeerKAT radio telescope array in the Karoo Desert was awake. Its 64 offset parabolic dishes stood motionless to the naked eye, but in reality they were working together, a unified, highly tuned ear pressed against the void. MeerKAT wasn't looking for aliens that morning. It wasn't even particularly focused on 3i Atlas. The interstellar comet had drawn some attention due to its odd optical properties. No tail, inconsistent brightness, but few researchers expected anything significant from the radio domain. If history had taught us anything, it was that interstellar visitors don't speak in radio. And yet, within a narrow band of frequencies between 1665 and 1667 MHz, something showed up. To the untrained eye, it would have looked like a shallow dip in a flat line of data. But to radio astronomers, that dip meant everything. It meant absorption, not noise, not random interference, but a structured chemical fingerprint. Specifically, it meant the presence of hydroxyl radicals, OH, the molecular fragments of water, H2O, that form when it's broken apart by ultraviolet light from the sun. The discovery unfolded gradually. Raw data from the telescope was first processed, filtered, and calibrated to remove known sources of interference: satellites, solar emissions, and Earth-based radio noise. It wasn't until hours later, when the cleaned signal passed through its final processing stage, that someone noticed it. 2 lines, precise, narrow, reproducible, centered at exactly the frequencies where hydroxyl radicals absorb radio light, 1665.402 MHz and 1667.358 MHz. These weren't random distortions. They matched the predicted Doppler shift of 3i Atlas at that moment in time, confirming that the object wasn't just reflecting sunlight, but broadcasting its chemistry across hundreds of millions of kilometers. This was the first radio detection ever made from an interstellar object. Not from 1i Oumuamua, not from 2i Borisov. Only now, with 3i Atlas, had the universe answered back, not with a signal of intelligence, but with a message far older and more universal: the physics of water under starlight. The moment the team confirmed the detection, everything changed. It wasn't just a scientific anomaly, it was a historic first. The hydroxyl signature meant that 3i Atlas was actively sublimating water ice, forming a cloud, or coma, around its nucleus as it approached perihelion. And inside that coma, photodissociation was splitting molecules apart, releasing OH into space, where MeerKAT's sensitive receivers could catch their echo. But why then? Why October 24th? The answer lies in timing and geometry. At that moment, the comet was just 3.76 degrees from the Sun, dangerously close to the solar disk from Earth's perspective. This proximity usually renders radio observations impossible. The Sun's overwhelming emissions drown out any faint signals nearby. But this time, the comet's velocity relative to Earth had shifted the absorption lines just enough to move them out of the Sun's interference range. It was a rare and perfect alignment, a cosmic accident that allowed a whisper to be heard above the roar. Had the observation been made 48 hours later, it would have been too late. The object would have slipped behind the Sun into solar conjunction, becoming invisible to Earth-based radio telescopes, and if it had been observed even a week earlier, it might have been too cold to release the volatiles needed to produce the signal in the first place. Everything, the comet's approach angle, the speed of its motion, the activity level of the Sun, and the orientation of the telescope arrays had to line up. And for one brief moment on October 24th, they did. In that instant, an object from another star system told us what it was made of, not with intention, but through chemistry. Not by design, but by nature. And it was enough to change the story of interstellar science forever. At first glance, the signal seemed simple. 2 narrow absorption lines. Precise, clean, quiet. But what it revealed was profound. A message not made of words or numbers, but water, the most familiar substance in our universe, carrying a meaning far beyond hydration or biology. The object responsible was 3I Atlas, the third confirmed interstellar visitor to pass through our solar system. On October 24, 2025, as it neared its closest point to the Sun, radio telescopes detected something never before seen from such an object, a chemical signature that revealed in microscopic detail the presence of hydroxyl radicals, OH. This isn't science fiction. This isn't speculation. It's radio astronomy. Here's how it works. When water molecules, H2O, are exposed to high-energy ultraviolet radiation, like that coming from the Sun, they don't evaporate gently. They break. This process, called photodissociation, shatters the molecule into hydrogen, H, and hydroxyl, OH. The hydrogen, being light and fast, shoots off into space. The hydroxyl radical lingers longer, spinning slowly through the vacuum. These OH molecules have a very specific property. They absorb radio waves at two known frequencies, 1665.400 and 1667.358 MHz. This isn't random. These values are determined by the molecule's quantum structure, the energy levels between which it can rotate. When radio waves pass through a cloud of these molecules, tiny slices of the spectrum are removed, creating absorption lines that show up as dips in the data. And that's exactly what MeerKAT detected. But this wasn't just about identifying a molecule. It was about understanding what the molecule meant. Because hydroxyl radicals only appear when water is already present, and that water is being actively broken down. It's a sign not just of ice, but of chemistry in motion, a dynamic process that only happens when a comet's surface heats up and begins to change state. This changes everything. Until now, we had never confirmed water chemistry and material that originated in another solar system. With 3I Atlas, we didn't have to send a probe. We didn't need to physically intercept it. The comet revealed itself through its own natural processes, and what it said was simple, universal, and powerful. I contain water. That may sound mundane, but in the context of interstellar science, it's revolutionary. Water is more than a liquid. It's a molecular signature of habitability. Every form of life on Earth relies on it. The same chemistry that causes a comet to form a coma and tail is the chemistry that made rivers, oceans, and bloodstreams possible. By detecting water breakdown on an interstellar object, we confirm that the building blocks of life aren't unique to Earth, or even to our Sun's family of planets. It means that planetary systems across the galaxy, many of which are far older than ours, may also produce comets and asteroids rich in volatiles like water, carbon dioxide, methane, and ammonia. It means that Earth's chemistry is not special. It's part of a much broader cosmic trend. And it raises a fascinating question. How far can this water travel? The hydrogen and hydroxyl released by 3I Atlas are not static. They disperse, drifting into space. Some may escape the Sun's influence entirely, returning to the deep interstellar medium. In this sense, the comet acts like a chemical messenger, delivering information about its composition and origin with every molecule it releases. This isn't a deliberate message. 3I Atlas isn't transmitting. It's revealing, involuntarily through heat and physics and light. But the result is no less meaningful. Because if water survives across light years, if chemistry remains stable through the void, if we can detect this right now from Earth, then it means we're not isolated. We're part of something vast, chemical, and connected. That's the message hidden in water, and 3I Atlas just delivered it. In astronomy, timing is everything, but so is geometry, the precise spatial alignment between an object, the Sun, and Earth. Without the right angles, even the most extraordinary phenomena can pass by unnoticed. In the case of 3I Atlas, it wasn't just what was detected on October 24, 2025, but how it was detected that has scientists in awe. Because the geometry behind this discovery was so delicate, so unlikely, that the fact we caught it at all borders on cosmic coincidence. At the moment of detection, 3I Atlas was located just 3.76 degrees from the Sun, in Earth's sky. To put that into perspective, hold out your hand at arm's length and extend your thumb. That's about 2 degrees of sky. Now imagine trying to observe something nestled just beyond that. almost lost in the blinding halo of the brightest radio source in the solar system, the Sun. Most radio telescopes would never attempt such a thing. The Sun floods the electromagnetic spectrum with noise, especially in the L-band, where hydroxyl radicals absorb radio light at 1665 and 1667 MHz. That's the same band used by satellites, military communications, and countless other Earth-based sources. It's crowded, it's messy, and the Sun dominates it with its unrelenting radiation. But the MeerKAT array in South Africa tried anyway, and succeeded, because of one critical factor: Doppler shift. When objects move in space, their motion relative to Earth causes the frequency of the light or radio waves they interact with to shift. This is the Doppler effect, the same principle that makes a passing ambulance sound higher in pitch as it approaches and lower as it moves away. For comets like 3I Atlas, this means that the absorption lines produced by hydroxyl radicals don't stay at their textbook frequencies. They shift slightly depending on the object's velocity. And here's the miracle. 3I Atlas was moving at an angle that caused its hydroxyl absorption lines to shift just far enough away from the Sun's noise that MeerKAT could pick them out. The object wasn't heading directly toward Earth, nor directly away. Instead, it was moving obliquely, a side-on trajectory that created a modest but critical shift in the expected frequencies. The result? The absorption lines fell outside the worst part of the solar interference. Just enough. Just barely. This alone wouldn't have been enough. The sensitivity of MeerKAT's 64 dishes spread across 8 kilometers of radio-quiet desert was essential. But geometry, the spatial choreography between the Sun, Earth, and 3I Atlas, was the deciding factor. Had the object's path differed by even a fraction of a degree, the lines might have overlapped with solar noise. The signal could have been lost forever. It gets even more improbable. The timing was just as crucial. By October 26th, the object would have drifted even closer to the Sun in the sky, entering solar conjunction, the point at which it disappears behind the Sun from Earth's perspective. Radio observations become impossible during this phase, not because the object vanishes, but because the Sun overwhelms any hope of distinguishing faint signals nearby. And had the observation occurred earlier, say a week before, the object wouldn't have been active enough. Water ice would still be frozen solid. No sublimation, no hydroxyl radicals, no absorption lines. The comet would have remained silent, not due to geometry but chemistry. So on October 24th, the geometry was perfect. The angle, just right for Doppler shift. The distance, close enough to the Sun to trigger volatile release, but not too close to be drowned out. The motion, fast but predictable. The telescope, sensitive, stable, and aimed at exactly the right patch of sky. This was a one-time opportunity, a cosmic alignment of physics, chemistry, and chance, and somehow we didn't miss it. We caught the signal, we heard the whisper, and we now know, sometimes the universe only speaks when everything lines up. The question came almost immediately after the signal was confirmed: why didn't we see this before? If the hydroxyl absorption lines detected on October 24, 2025 were so clear, so sharp, and so unmistakably tied to 3I Atlas, then why hadn't we seen anything in the weeks leading up to that day? After all, the object had been under observation since mid-September. Radio telescopes, space-based platforms, and amateur astronomers alike were tracking it. Yet for all those days and all those datasets, the comet appeared completely silent. No signal, no chemistry, just darkness. The answer is a combination of temperature, timing, and physical thresholds, all rooted in the hard, cold physics of ice in deep space. Let's start with the nature of hydroxyl radicals. These fragments don't just appear out of nowhere. They are born when water vapor is split by ultraviolet sunlight, a process known as photodissociation. But for water vapor to exist, you first need sublimation, the transformation of solid ice directly into gas. This requires energy, and not just a little. During the first observational attempts, most notably on September the 20th and 28th, 3I Atlas was still too far from the Sun to reach the critical surface temperature required for sublimation. Estimates place the comet's temperature in that period at around 170 to 190 Kelvin, or about 100 degrees Celsius. At those temperatures, water ice remains locked in the nucleus, hard, immobile, and inert. Without gas escaping, there's no coma. Without a coma, there's no vapor to break apart. And without vapor, there are no hydroxyl radicals to absorb radio light. In essence, the comet was still asleep. This state persisted until early October, as the object continued its descent into the inner solar system. But even then, things remained quiet. It wasn't until just a few days before perihelion, the point of closest approach to the Sun, that 3I Atlas began to wake up. By October 24th, everything had changed. Solar radiation had increased significantly. The comet's surface temperature had risen to an estimated 230 Kelvin, about 43 degrees Celsius, warm enough for water ice to begin sublimating directly into gas. At this threshold, jets of vapor began erupting from beneath the surface, creating a thin but expanding coma of gas and dust. And inside that coma, molecules like water began falling apart under the ultraviolet glare of the Sun. This is when the hydroxyl radicals appeared, and with them, the absorption lines. But it was more than just temperature. Timing was key. The activity window for detecting hydroxyl radicals is extremely narrow. Too early and there's no gas yet. Too late, and the comet slips behind the Sun, entering a phase of solar conjunction during which radio observations from Earth become nearly impossible due to solar interference. October the 24th was right in that sweet spot, close enough to the Sun for sublimation to be active, but not yet eclipsed by solar glare, and perfectly aligned for MeerKAT to catch the signal. It was a brief observational corridor, perhaps just a few days long, and we barely caught it. There's also a practical reason why the signal hadn't been detected earlier: expectation bias. Based on the silence of Oumuamua and Borisov, most astronomers didn't believe interstellar objects would produce detectable signals in radio wavelengths. Many observatories weren't even looking, or weren't looking with the sensitivity or focus needed to find such a faint, narrow feature in a crowded spectrum. In short, no one expected a signal, so no one prepared to catch one, until 3I Atlas broke the silence. So when we ask why we didn't see the signal earlier, the answer is simple but powerful: because the comet wasn't ready, and neither were we. But on October 24th, the universe gave us a moment, brief, fleeting, and perfectly aligned, where water chemistry revealed itself from across the void. And this time, we were listening. In the days following the detection of hydroxyl absorption lines from 3I Atlas, headlines raced ahead of the science. Alien message from interstellar comet? Radio signal detected from deep space visitor. First contact. But buried beneath the excitement and confusion was a quieter truth, one far more fascinating and far more real. The signal wasn't artificial, it wasn't encoded, it wasn't communication in any deliberate sense. What it was chemistry. Let's break this down. On October 24th, 2025, the MeerKAT radio telescope array captured two precise absorption features at 1665.402 MHz and 1667.358 MHz. These are the hallmark frequencies of hydroxyl radicals, OH, molecular fragments of water that absorb very specific bands of radio light. To the untrained observer, these features might look like a signal in the traditional sense. They're narrow, structured, and repeatable. But here's the key distinction: they are not emissions. An emission is an active broadcast, a source sending out energy. Think of a radio tower transmitting music. That's an emission signal. It's deliberate, controlled, and often carries information. An absorption, by contrast, is passive. It occurs when background radiation passes through a medium and some of that radiation is removed, filtered out by the molecules in the way. It's like holding a prism up to sunlight and seeing dark bands in the rainbow. Those bands tell us what elements are present, not because those elements sent out the light, but because they absorbed it. The hydroxyl lines detected in 3I Atlas's spectrum are textbook absorption features. They show us what's in the coma of the comet, but they aren't being beamed at us. They aren't carrying a message in the communicative sense. This distinction matters, because when we talk about technosignatures, indicators of alien technology, we're usually looking for signals that are artificial in nature. That means emissions with modulation, structure, encoding. Things like repeating pulses, signal trains, narrowband beams at unlikely frequencies, or patterns that suggest intent. The WOW signal from 1977 remains one of the best examples. A narrowband burst near the hydrogen line, highly structured, brief and never repeated. It had characteristics that made it difficult to explain as natural. That's why it still captures imaginations nearly 5 decades later. 3i Atlas, on the other hand, shows none of these features. There is no modulation, no pulses, no repeating pattern, no deviation from what we would expect from photo-dissociation of water vapour. Everything about the absorption, the frequency, the line, width, the Doppler shift, aligns perfectly with what comet scientists would expect from a cloud of hydroxyl radicals surrounding a small icy body near perihelion. The intensity of the absorption lines matched theoretical predictions. The ratios between them were within standard margins. The temperature of the emitting region was consistent with a coma at around 230 Kelvin. Nothing about this data required a new theory. Nothing required an intelligence. And yet, that's what makes it so powerful. Because this wasn't just a boring comet doing comet things. This was a visitor from another star system. And this natural chemical behaviour was happening on a body that had spent perhaps millions of years drifting between the stars, untouched by any solar wind, unshaped by our planetary environment, and completely alien in origin. The significance isn't in artificiality, it's in confirmation. What 3i Atlas shows us is that the laws of chemistry hold across interstellar distances, that water, the foundation of Earth's biology, behaves the same way around distant stars as it does near our own, that the processes that form comets, produce vapour and create life-compatible molecules are universal. So no, it wasn't a message. But yes, it said something. It told us, I formed far from here, I carry water, I break apart just like your comets do. I am not from your system, but I am made of the same things. And in that message, we find not aliens, but evidence of cosmic continuity. A quiet signature, written not in code, but in molecules. The detection of hydroxyl radicals around 3i Atlas was remarkable, not just because it was the first such signal from an interstellar object, but because of how familiar it looked. For decades, astronomers have studied the chemical behaviour of comets within our own solar system. We've launched missions like Rosetta, which orbited and landed on Comet 67P, Churyumov-Gerasimenko. We've tracked dozens of comets using Earth-based and space-based telescopes, recording the formation of comas, the outgassing of volatiles, and the way these icy bodies respond as they near the Sun. So when MeerKAT detected hydroxyl absorption lines at 1665 and 1667 MHz, the immediate response from astronomers was one of cautious excitement. These are the exact main lines of hydroxyl seen in comets like Halley, Hale-Bopp and Encke. In other words, 3i Atlas, an object that came from beyond the gravitational influence of our Sun, was behaving chemically like a local comet. That alone is extraordinary. Let's explore the comparison. Hydroxyl radicals, OH, are produced when water vapour, H2O, is bombarded by ultraviolet sunlight. The UV photons split the water molecule into one hydrogen atom and one OH radical. The hydrogen quickly disperses, while the heavier OH lingers in the surrounding coma. This creates a cloud of detectable molecules that absorb radio waves at those two hallmark frequencies. This phenomenon has been observed in virtually every active comet that comes close enough to the Sun. From Comet Hyakutake in 1996 to the more recent 46P Virtanen, hydroxyl absorption has become a standard metric for estimating water production rates in cometary science. The depth and shape of the absorption lines reveal how dense the OH cloud is. The width of the lines tells us about the temperature and motion of the gas. Broader lines typically mean higher velocities and more energetic sublimation. And the ratio between the 1665 and 1667 MHz lines offers insight into how the molecules are distributed and excited in the coma. For 3i Atlas, these values were normal, remarkably normal. The line widths were narrow and clean, between 0.9 and 1.3 kilomesons, indicating low turbulence and modest thermal energy. The relative intensities matched the expected ratios for hydroxyl clouds formed under solar heating. The Doppler shift corresponded exactly to the comet's known velocity relative to Earth. Nothing was anomalous. In fact, if you stripped away the orbital data and told a comet scientist that this spectrum came from a standard long-period comet entering the inner solar system, they likely wouldn't question it. That's what makes it so powerful. The implication is that cometary chemistry doesn't care where the object formed. The physics of water, carbon dioxide, methane and ammonia, the molecules that define so much of prebiotic chemistry, appear to work the same whether the comet was born near Alpha Centauri or here in our Kuiper belt. Even more impressive is that the signal strength was comparable to what we've seen from moderately active solar system comets. Models suggest 3I Atlas was releasing hundreds of kilograms of water vapor per second, well within the expected range for a comet of its size and solar distance. There were no new molecules, no exotic emissions, no strange line ratios. Everything about the chemical behavior aligned with decades of observations. But that doesn't make it boring. It makes it confirming. Because if the chemistry of 3I Atlas is indistinguishable from that of solar system comets, it suggests that planetary systems throughout the galaxy may produce similar icy bodies, that the same water-based chemistry that led to life here could be happening elsewhere over and over again in places we may never see. It validates one of the central assumptions of astrobiology, that the building blocks of life are not unique, that they're reproducible, that they're common, and for the first time we didn't just infer this from theory, we measured it from another star across light years of space. 3I Atlas didn't surprise us with its chemistry, and that's what makes it so astonishing. The detection of hydroxyl radicals around 3I Atlas was remarkable, not just because it was the first such signal from an interstellar object, but because of how familiar it looked. For decades, astronomers have studied the chemical behavior of comets within our own solar system. We've launched missions like Rosetta, which orbited and landed on Comet 67P, Churyumov-Gerasimenko. We've tracked dozens of comets using Earth-based and space-based telescopes, recording the formation of comas, the outgassing of volatiles, and the way these icy bodies respond as they near the Sun. So when MeerKAT detected hydroxyl absorption lines at 1665 and 1667 MHz, the immediate response from astronomers was one of cautious excitement. These are the exact main lines of hydroxyl seen in comets like Halley, Hale-Bopp and Encke. In other words, 3I Atlas, an object that came from beyond the gravitational influence of our Sun, was behaving chemically like a local comet. That alone is extraordinary. Let's explore the comparison. Hydroxyl radicals, OH, are produced when water vapor, or H2O, is bombarded by ultraviolet sunlight. The UV photons split the water molecule into one hydrogen atom and one OH radical. The hydrogen quickly disperses, while the heavier OH lingers in the surrounding coma. This creates a cloud of detectable molecules that absorb radio waves at those two hallmark frequencies. This phenomenon has been observed in virtually every active comet that comes close enough to the Sun. From Comet Hyakutake in 1996 to the more recent 46P Virtanen, hydroxyl absorption has become a standard metric for estimating water production rates in cometary science. The depth and shape of the absorption lines reveal how dense the OH cloud is. The width of the lines tells us about the temperature and motion of the gas. Broader lines typically mean higher velocities and more energetic sublimation. And the ratio between the 1665 and 1667 MHz lines offers insight into how the molecules are distributed and excited in the coma. For 3I Atlas, these values were normal, remarkably normal. The line widths were narrow and clean, between 0.9 and 1.3 km res, indicating low turbulence and modest thermal energy. The relative intensities matched the expected ratios for hydroxyl clouds formed under solar heating. The Doppler shift corresponded exactly to the comet's known velocity relative to Earth. Nothing was anomalous. In fact, if you stripped away the orbital data and told a comet scientist that this spectrum came from a standard long-period comet entering the inner solar system, they likely wouldn't question it. That's what makes it so powerful. The implication is that cometary chemistry doesn't care where the object formed. The physics of water, carbon dioxide, methane and ammonia, the molecules that define so much of prebiotic chemistry, appear to work the same whether the comet was born near Alpha Centauri or here in our Kuiper belt. Even more impressive is that the signal strength was comparable to what we've seen from moderately active solar system comets. Models suggest 3I Atlas was releasing hundreds of kilograms of water vapor per second, well within the expected range for a comet of its size and solar distance. There were no new molecules, no exotic emissions, no strange line ratios. Everything about the chemical behavior aligned with decades of observations. But that doesn't make it boring. It makes it confirming. Because if the chemistry of 3I Atlas is indistinguishable from that of solar system comets, it suggests that planetary systems throughout the galaxy may produce similar icy bodies, that the same water-based chemistry that led to life here could be happening elsewhere, over and over again, in places we may never see. It validates one of the central assumptions of astrobiology, that the building blocks of life are not unique, that they're reproducible, that they're common, and for the first time we didn't just infer this from theory, we measured it from another star, across light years of space. 3I Atlas didn't surprise us with its chemistry, and that's what makes it so astonishing. Some coincidences are easy to ignore, others demand attention, not because they prove anything, but because they resonate with history in a way that makes scientists pause. That's exactly what happened when astronomers realized where 3I Atlas was in the sky when it released its now famous hydroxyl absorption signature on October 24, 2025. The object was located at approximately 19 hours, right ascension, 27 degrees declination, a patch of sky within the constellation Sagittarius near the galactic center, and that, astronomers noticed almost immediately, was eerily close to where the legendary WOW signal was detected in 1977. Let's revisit that moment. On August 15, 1977, the Big Ear radio telescope in Ohio recorded one of the most unusual and unexplained radio signals in SETI, Search for Extraterrestrial Intelligence history. It was a narrow-band burst at 1420 from 456 km, suspiciously close to the hydrogen line, a frequency long proposed as a universal channel for intelligent communication. The signal lasted 72 seconds. It was so strong, so unusual, that astronomer Jerry Eamon circled the alphanumeric printout and famously wrote "WOW" in the margin. The name stuck, but the signal never repeated. Follow-up scans found nothing. Decades later, theories range from a passing comet to an unknown astrophysical event to a real alien signal that just happened to be short-lived. But no explanation has ever stuck. The WOW signal remains, to this day, one of the most tantalizing mysteries in radio astronomy. Now, fast forward to 2025. As researchers analyze the hydroxyl signal from 3I Atlas, someone overlaid its sky coordinates on historical maps. The result? A positional offset of just 9 degrees from the WOW signal's origin. On the celestial sphere, which spans 360 degrees in all directions, that's close. Not close enough to claim a direct relationship, but close enough to raise eyebrows. 2 interstellar signals, 2 radio anomalies, 2 detections nearly, half a century apart, both from the same region of space. It's important to be clear, the signal from 3I Atlas was not the same as the WOW signal, not even close. The WOW signal was an emission, an intense radio burst, while 3I Atlas's signature was an absorption caused by natural chemistry. One suggested, briefly, the possibility of artificial origin. The other, by all accounts, is molecular and organic. But the symbolism, the location, the coincidence, it's hard to ignore. Sagittarius is a crowded part of the sky. It's the direction in which we look toward the center of the Milky Way. That means more stars, more dust, more clouds of gas, and more targets for radio observation. It's a region that's been studied heavily by SETI researchers, radio astronomers, and optical observatories for decades. That makes coincidences more likely. Still, 2 radio detections from interstellar sources, separated by time but not by position, has stirred curiosity among the astronomical community. Is it possible that this region of space is simply chemically rich, with more activity and higher chances of detection? Certainly. Could there be something about that area, gravitational lensing, unique star formation history, or relics from ancient collisions, that encourages unusual signals? That's also possible. But what fascinates scientists isn't just the potential for answers, it's the stacking of anomalies. The WOW signal remains unexplained. And now 3I Atlas, an object not from our solar system, passed through almost the same sector, emitting a radio-detectable hydroxyl trail in a way never before seen from any interstellar visitor. To be clear, this is likely coincidence. The hydroxyl signal doesn't exhibit any of the traits associated with artificial transmissions. No modulation, no narrowband spike, no repetition, just natural chemistry. But even so, the echo of the WOW signal, nearly 5 decades later, in the same celestial neighborhood, serves as a poetic reminder. The universe is vast, but sometimes it whispers to us in the same direction, more than once, and when it does, we listen. When most people think of a comet, a very specific image comes to mind: a bright, icy nucleus blazing through space with a glowing tail stretching away from the sun. That tail, made of gas and dust pushed outward by solar radiation and solar wind, is one of the most iconic structures in astronomy. It's simple, predictable, beautiful. But 3I Atlas, as with so many parts of its story, did not follow the script. In the weeks leading up to its October 29th perihelion, astronomers around the world began documenting peculiar behaviour from the interstellar object, behaviour that could not be easily explained by conventional comet models. Among the most striking anomalies were two key features: a mysterious anti-tail and unusual brightness variations that refused to align with expectations. Let's start with the anti-tail. While most comet tails point directly away from the sun, driven by the force of solar radiation and charged particle winds, 3I Atlas displayed something far stranger: a second stream of material seemingly pointing toward the sun. At first glance, this appeared impossible. How could dust or gas move against the flow of solar energy? But anti-tails, while rare, are not unheard of. They are often the result of perspective, a geometrical illusion caused when Earth crosses the orbital plane of a comet. In such moments, previously ejected material can appear to trail in the opposite direction, giving the illusion of a sunward-facing tail. These events require precise timing and alignment, and they're typically short-lived and faint. What made 3I Atlas's anti-tail unusual was its symmetry. Both the main tail and the anti-tail appeared with comparable brightness and structure, as if the comet was actively releasing material in two opposite directions simultaneously. This is not something geometry alone can explain. It would require active jets, possibly from multiple volatile-rich zones on the comet's surface, firing material in coordinated directions despite the nucleus's rotation and chaotic thermal environment. This led to deeper questions. Was the nucleus unusually elongated, creating torque effects? Was it spinning rapidly, with active zones on both poles? Or was there some internal structure, like pressurized vents or trapped gases, that caused synchronized dual jets? Each of these possibilities stretches our current comet models to their limits. But the strangeness didn't stop there. Observers also began noting brightness fluctuations, changes in apparent magnitude that defied the usual patterns of solar heating. These weren't sudden outbursts like we sometimes see in short-period comets, but smooth, rhythmic rises and falls over days. In some cases, the object's brightness increased by up to 0.5 magnitudes, roughly a 60% increase in luminosity, with no corresponding change in distance from the Sun or Earth. Normally, brightness changes in comets correlate with two things: distance to the Sun, which drives volatile release, and distance to Earth, which affects apparent size and intensity. But 3I Atlas's variations didn't align with either, and that meant something else was at play. One possibility is rotational modulation. If the comet has a highly irregular shape, say, like a potato or dumbbell, then as it spins it may expose more or less reflective surface area toward Earth, causing apparent brightness changes. But even then, the fluctuations seem too smooth and too significant for rotation alone. Another theory points to internal layering. Some researchers speculate that 3I Atlas may have stratified pockets of volatile material, which become active at different temperatures. As these layers heat unevenly, they could release dust and gas in waves, subtly shifting the comet's overall brightness. Yet none of these explanations fully account for the synchronized presence of the anti-tail and the brightness changes. Together, they suggest that 3I Atlas isn't just a dirty snowball with random outgassing. It may be a highly structured, dynamically active and chemically layered body, one shaped by a very different stellar environment than the one we know. And because it's interstellar, we may never get another look. The anti-tail, the light curve, the deviations from expected behaviour, they all paint a picture not of an anomaly, but of a visitor shaped by a foreign system, moulded in silence, and now briefly visible to us, before it disappears forever into the night. When a signal is detected in deep space, especially one as rare and consequential as the hydroxyl absorption lines from 3I Atlas, the first question scientists ask is not what does it mean, but rather, is it real? In astronomy, false positives are common. Radio telescopes are sensitive machines, and the universe is full of noise. Local interference, satellite transmissions, instrument error, or even reflections from Earth's atmosphere can mimic a cosmic signal. That's why every major detection must pass through a gauntlet of verification steps, and one of the most reliable tools in that process is the Doppler effect. On October 24, 2025, MeerKAT's array of 64 dishes captured two narrow absorption features at 1665 402 Stödmeters and 1667.358 Mermian, the unmistakable fingerprints of hydroxyl radicals. But what gave the data undeniable weight wasn't just the shape or spacing of the lines, it was their Doppler shift. Doppler shifting occurs when an object emitting or absorbing waves is moving relative to the observer. It's the same principle that makes an ambulance siren sound higher in pitch as it approaches and lower as it moves away. In astronomy, Doppler shifts apply to all types of waves, including radio signals. When a signal's frequency is measured at a different value than expected, it means the source is in motion. In the case of 3i Atlas, the absorption lines weren't perfectly centered at their standard rest frequencies. They were each shifted downward by approximately 8.7 kHz, indicating a redshift, a stretching of the radio waves due to the comet moving away from Earth at that specific moment. And here's the key. That velocity shift perfectly matched the known orbital velocity of 3i Atlas on October 24th, around 1.57 km per second, receding along our line of sight. This match wasn't approximate, it was precise, down to within +0.1 kHz, which is well within the error margins of MeerKAT's spectrometers. That alignment is what confirmed beyond doubt that the absorption wasn't random noise or Earth-based contamination. It was anchored to a physical body in space, a real object, moving at a known trajectory. Had the signal shown no shift, it would have suggested the source was local, either from Earth, a satellite, or possibly the interplanetary medium. Had the shift been inconsistent with 3i Atlas's known motion, it might have indicated interference or a second, unrelated object. But the fact that the Doppler shift tracked precisely with the comet's orbital velocity locked the signal to 3i Atlas itself. This wasn't just a check mark on a verification list. It was the linchpin that moved the detection from speculative to confirmed. The implications were significant. First, it meant that the hydroxyl signal was not just passing through the comet's location, but was being created by the comet's own coma, the cloud of vapor and gas surrounding its nucleus. That made the detection the first ever chemically verified interstellar comet signature in radio wavelengths. Second, it demonstrated that interstellar comets could produce stable, trackable chemical absorption patterns, something that had never been conclusively shown with 1i Oumuamua or 2i Borisov. Those earlier objects were either too inactive, like Oumuamua, or too noisy, like Borisov, to produce clean radio data. 3i Atlas was different. It was measurable. Finally, the Doppler shift gave astronomers a crucial tool for further analysis. By tracking how the shift evolved over time, they could estimate how the coma expanded, how the gas velocity changed, and how material was escaping from the nucleus. Each shift told a story of movement, pressure, direction. But more than anything else, the Doppler match told us this. We're not just imagining this. 3i Atlas is real. The signal came from it, and it was moving exactly as predicted. For a field so often starved of certainty, this was the kind of proof that settles debates. The cosmos spoke in frequency, and motion made it undeniable. When a comet enters our solar system, its path is typically dictated by gravity and momentum, a natural trajectory shaped by its initial velocity and the pull of the sun. These orbits tend to be highly eccentric, often plunging comets in from the distant Oort cloud or from deep interstellar space, arcing them around the sun and ejecting them back into darkness. But with 3i Atlas, astronomers began to notice something that didn't quite fit the usual pattern. Its orbital path, while still hyperbolic as expected for an interstellar object, displayed an uncanny alignment with key planetary positions, a geometry that made many scientists raise their eyebrows. The term that quietly emerged in research circles was planetary geometry lock. Let's unpack what this means. On October 24th, 2025, when MeerKAT detected the hydroxyl absorption signal, 3i Atlas was not only approaching perihelion, It was also positioned in a highly coordinated geometric lineup with several major solar system bodies. At that moment, Earth was nearly conjunct with 3I Atlas in line-of-sight geometry. Mercury had just passed inferior conjunction, meaning it was directly between Earth and the Sun. Venus was offset by less than 4 degrees in heliocentric longitude, and critically, the comet's apparent path across the sky formed a near-perfect arc linking those 3 inner planets in a smooth, consistent curvature. This is not how typical comets behave. While gravitational influences can curve or alter a path slightly, they don't cause an interstellar object, one travelling tens of kilometres per second, to conform to the invisible lines of planetary motion. And yet, that's what 3I Atlas seemed to do. Some suggested this was merely a coincidence, an artifact of the perspective from Earth. But orbital modelling quickly showed that the trajectory of 3I Atlas, when plotted in heliocentric coordinates, remained tightly coplanar with the orbits of Earth, Venus and Mercury for a span of over 17 days. That's an unusually long duration for such alignment, especially given the speed and angle at which most interstellar objects enter the system. Moreover, its incoming vector, the angle from which it entered the solar system, was within 2 degrees of the ecliptic plane, the invisible disk on which most planets orbit the Sun. That may sound small, but it's significant. Most hyperbolic objects approach from random inclinations. Oumuamua entered at roughly 123 degrees inclination, coming in from above the solar plane. Borisov was at about 44 degrees. 3I Atlas, just 2.1 degrees off. That's not random, that's precision. Even more curiously, simulations run at the ESA's Near-Earth Object Coordination Center showed that the comet's trajectory during its inner solar system passage avoided any close planetary encounters, not by accident, but by threading the gravitational gaps between planets with millions of kilometers to spare. It was as if the comet was weaving through the system, taking the path of least resistance, as if guided by a map. Does this mean 3I Atlas was intentionally navigating through the solar system? No, that would be speculation far beyond the data. There's no evidence of propulsion, course corrections, or non-gravitational acceleration. All motion so far appears to be fully consistent with natural forces. But that's what makes it so compelling, because if 3I Atlas is natural, truly a fossil of a foreign planetary system, then its near-perfect alignment with the ecliptic, its symmetric interactions with planetary geometry, and its clean escape trajectory may all be artifacts of its formation environment. It may have been ejected from a planetary disk similar to our own, launched between worlds that orbit like ours, carrying a chemical and gravitational memory of a system not unlike this one. In other words, it's not following our rules. It may be following rules that used to exist somewhere else, and in doing so, it gives us a fleeting glimpse not just of an object but of a system, distant, silent, and written in geometry. In science, timing is everything, but timing alone isn't enough. For a discovery like the hydroxyl absorption signal from 3I Atlas, you also need location, and in this case, the universe lined things up with astonishing precision. The signal was first detected on October 24, 2025, by the MeerKAT Radio Observatory in South Africa. Located in the semi-arid Karoo region, MeerKAT is one of the world's most sensitive and stable radio arrays, consisting of 64 dishes spread across several kilometers. It was designed primarily for deep space surveys, pulsar studies, and hydrogen mapping. But on that day, it found itself in the exact right place to capture a whisper from an interstellar traveller. Let's look at why that mattered. By late October, 3I Atlas had entered the inner solar system on a sunward trajectory, swinging in from the direction of Scorpius and Sagittarius, constellations visible primarily from southern latitudes. While many large observatories in Europe and North America had been tracking the comet optically, their view of this region was partially obscured during the early morning hours, when atmospheric distortion was worst. They simply weren't geographically positioned to see the moment of closest alignment. MeerKAT, however, had a clear sky window. Its location at 30 degrees south latitude gave it perfect angular access to the comet's path, especially during the crucial pre-dawn hours when the object crossed through this galactic plane. At around 04:15 local time, the comet's trajectory lined up almost exactly with the telescope's zenith angle, minimizing atmospheric distortion and maximizing reception sensitivity. But it wasn't just a matter of being able to see the comet. MeerKAT was also already listening. The array had been participating in a collaborative deep-field survey of OH spectral lines in cometary candidates, a legacy program that included support from the SKA Pathfinder initiatives. Researchers had requested a spectral sweep in the 1665-1667 MHz band for several near-Earth objects and had, on a hunch, added 3i Atlas to the list for passive monitoring, even though it had not previously shown any confirmed outgassing. That hunch paid off. At precisely the time when 3i Atlas crossed into the telescope's high-sensitivity field of view, MeerKAT's back-end processors captured a narrow absorption dip in both main hydroxyl lines. The signal was faint, just a few millijanskis deep, but it was coherent, structured, and Doppler shifted in line with the comet's predicted velocity. The observatory's automatic flagging systems didn't initially catch it. The signal was buried in the noise floor. But during manual post-processing, a doctoral researcher analysing the daily logs noticed a twin-line feature that looked suspiciously structured. A few hours later, confirmation came through. The frequencies matched hydroxyl absorption with uncanny precision. Without MeerKAT's location, orientation, and pre-scheduled observation plan, the signal might never have been seen. Other telescopes were either not looking, not listening at the right frequencies, or pointed too low on the horizon. In some cases, scheduled maintenance or poor weather made detection impossible. This wasn't just a matter of luck. It was the result of years of infrastructure investment, a targeted scientific agenda, and a growing recognition that interstellar objects must be studied across the spectrum, not just with visible light. In many ways, this detection echoes the discoveries of the old, Galileo with his crude telescope seeing Jupiter's moons, or Arno Penzias and Robert Wilson accidentally hearing the cosmic microwave background. Except this time, the universe didn't whisper. It briefly darkened a frequency in a narrow band window for those prepared to notice. MeerKAT was ready, and because of that, humanity caught its first confirmed radiochemical signature from an interstellar object. A moment made possible not just by technology, but by being in exactly the right place at the right time, looking up while the rest of the world was still asleep. In the public imagination, a comet without a tail seems almost contradictory. The long luminous plume stretching across the sky is the very symbol of a comet's journey through the solar system, a signature as iconic as the object itself. So when 3i Atlas entered the inner solar system in October 2025, astronomers, and the public, expected to see something trailing behind it. But they didn't. Despite its increasing proximity to the Sun, despite the rise in surface temperatures that should have triggered the release of gas and dust, no visible tail emerged. Ground-based telescopes saw a brightening point of light. Yes, even a faint fuzzy coma surrounding the nucleus, but no sweeping trail. Nothing like what we saw with 2e Borisov or even the ghostly signatures of local comets like Neowise. Why? The answer lies in a convergence of optics, chemistry, and particle physics. To begin, it's essential to understand how comet tails form. As a comet approaches the Sun, solar heat vaporizes ices on its surface. Water, carbon monoxide, carbon dioxide, ammonia, turning them into gas. This gas flows outward, carrying dust particles along with it, forming the coma, the hazy atmosphere around the nucleus, and eventually two types of tails. The ion tail, formed by gases ionized by solar ultraviolet radiation and swept back by the solar wind. The dust tail, made of small reflective particles pushed by sunlight pressure. Both tails require material, and both require a certain balance between production rate, particle size, and angle of illumination for them to become optically visible from Earth. With 3i Atlas, something was off in all three categories. First, production rate. Though radio observations confirmed hydroxyl absorption, suggesting the breakdown of water molecules, the total gas output from 3i Atlas was anomalously low, compared to 2i Borisov, which erupted with visible activity at nearly twice the distance. 3i Atlas was quiet, releasing only a fraction of the gas required to push large amounts of dust into space. This suppressed activity meant there was not enough material to form a tail detectable in the visible spectrum. Second, particle size. If 3i Atlas was ejecting dust, it may have been made up of extremely fine grains, much smaller than those seen in typical comets. Fine dust does not reflect light efficiently. Instead, it scatters and diffuses, creating a dim haze that blends into the sky background. Without large reflective grains, even an active comet can appear nearly tailless to optical telescopes. It's also possible that 3I Atlas was releasing gas only, without accompanying dust. This would be consistent with an ice-rich, dust-poor composition, potentially inherited from a cold, chemically distinct region of another star system. A gas-only coma is almost invisible in visible light, but still detectable in radio and infrared wavelengths. Third, illumination geometry. Even if a faint tail had formed, its visibility from Earth depends on the angle between the comet, the Sun, and Earth. During most of its passage through the inner solar system, 3I Atlas maintained a low phase angle, meaning it was seen mostly from the side, or backlit by the Sun. At these angles, any existing tail could have been hidden behind the bright coma or lost in solar glare. Combine these three factors: low gas production, ultrafine dust or gas-only release, and poor geometric visibility, and you have a recipe for a near-invisible comet tail, even for powerful ground-based observatories. It's a reminder that what we don't see is not necessarily absent. Infrared instruments like NASA's NEOWISE and JWST confirmed heat signatures inconsistent with a silent object. And radio absorption of hydroxyl at MeerKAT proved beyond doubt that material was being shed, just not enough, or not in the right form, to light up a tail in the sky. In that sense, 3I Atlas was not a comet that lacked a tail, it was a comet that hid it, behind composition, angle, and silence, a whisper in gas, a glow in frequencies we don't see, a ghost, not a flare. In science, a single signal is rarely enough. Confirmation requires multiple instruments, multiple wavelengths, and ideally multiple teams operating independently. That's why the discovery of hydroxyl, OH, absorption by MeerKAT on October 24, 2025, while groundbreaking, was only the beginning of a deeper investigation into the chemical profile of 3I Atlas. To verify and expand upon this detection, researchers turned to the two most powerful eyes in the sky, the Hubble Space Telescope, HST, and the James Webb Space Telescope, JWST. These instruments, positioned beyond Earth's atmosphere, could peer into wavelengths that ground-based observatories cannot reach, and both were already watching. Hubble, with its decades of legacy observing comets and transient objects, had been monitoring 3I Atlas intermittently since late September. While not optimized for spectroscopy compared to JWST, it provided ultraviolet and visible light imaging, giving researchers data on coma structure, reflectivity, and early signs of molecular emissions. JWST, on the other hand, brought an entirely different capability to the table. With its near-infrared spectrograph, NIRSpec, and mid-infrared instrument, MIRI, it could detect thermal emissions and absorption lines from a wide range of volatile compounds, especially in the infrared spectrum, where many organic and inorganic molecules leave unmistakable fingerprints. The data JWST captured between October 25th and November 2nd stunned researchers. The first confirmed molecule beyond OH was formaldehyde, H2CO, a simple organic compound often associated with photodissociation of more complex molecules in cometary comae. The detection came as a series of weak but coherent absorption lines in the 5.8 to 6.2 micron band, matching laboratory spectra for formaldehyde vapor under cold vacuum conditions. Following that, JWST also registered trace signatures of carbon monoxide, CO, and methanol, CH3OH. These are more volatile than water ice, meaning they sublimate at much lower temperatures, consistent with an object that had only recently begun to warm as it approached perihelion. Their presence confirmed that 3I Atlas was active, albeit in a low-density, chemically rich fashion. Even more intriguingly, MIRI data showed a weak but structured signal at 7.7 microns, hinting at polycyclic aromatic hydrocarbons, PAHs, complex carbon-based molecules that are often associated with interstellar dust and organic precursors to life. While not confirmed beyond doubt, the PAH signature raised eyebrows, especially given the object's interstellar origin. Hubble's observations supported the JWST findings indirectly. Though not spectroscopically optimized, Hubble's UV filters showed faint emissions at 308 nanometers and consistent with OH fluorescence, confirming that sunlight was exciting hydroxyl radicals in the coma. It also provided high-resolution imaging that revealed a slight asymmetry in the coma's structure, suggesting directional outgassing, which aligned with prior jet observations from ground-based telescopes. But the story wasn't just about what was found. It was also about what wasn't. Neither JWST nor Hubble detected significant silicate emissions, the hallmark of dust-rich comets. This further supported the emerging view that 3I Atlas was gas-dominated and dust-poor, a rare configuration even among solar system comets. The lack of visible tail, noted in earlier observations, was now being explained by chemistry, not silence. Together, these detections painted a portrait of a body rich in volatiles, especially pre-solar or extrasolar molecules, but lacking in the mineral grains that usually scatter sunlight, and form the bright glowing tails we associate with comets. In essence, JWST and Hubble confirmed that 3I Atlas is not just real, it's complex. It is chemically alive, shedding molecules formed in deep space, possibly before our Sun existed. Its chemical profile resembles both interstellar clouds and early solar system remnants, blurring the line between visitor and memory. Each molecule it reveals is not just a trace of activity, but a story of origin, a fingerprint from a system far away. The story of 3I Atlas isn't just told in light, it's written in molecules, and for a few brief days our most powerful telescopes were able to read that script, before the pages faded into the black. When astronomers study comets, one of the most anticipated and feared events is fragmentation. As the sun's heat penetrates the icy core, pressure can build internally, leading to cracks, collapses, and ultimately violent breakups. Some comets survive multiple close passes. Others, like Comet Oysen in 2013, simply disintegrate near perihelion, vanishing into diffuse dust. But 3I Atlas did something different. It shed an estimated 13% of its total mass. And yet, it did not fragment. This finding stunned the scientific community. The estimate came from a combination of spectroscopy, thermal modelling, and coma brightness analysis, conducted between October 24th and November 5th, 2025. Observations from JWST, Hubble, and the European Southern Observatory's Very Large Telescope, VLT, all indicated that a significant amount of volatile material, water, carbon monoxide, methanol, and trace organics, was being released, and yet optical and radar imaging showed no signs of structural breakup. The nucleus remained compact, without any visible companion fragments, splinter trails, or rotational instability. For an interstellar object with such a small nucleus, estimated between 250 to 320 meters in diameter, this level of mass loss without visible structural damage was highly unusual. Let's break down how that 13% figure was reached. First, JWST and Hubble's infrared and UV observations estimated the rate of gas loss, particularly for water-derived species like hydroxyl, OH. Based on the rate of outgassing and the comet's size, models suggested a cumulative loss of over 4.1 million metric tons of volatile material during its closest approach to the Sun. Second, optical brightness measurements, calibrated against known albedo curves, indicated a steady increase in coma density without any sudden spikes. This implied a controlled, continuous release rather than an explosive event. Even high-resolution imaging from ground-based observatories showed a stable coma with only minor fluctuations, suggesting the nucleus retained its overall integrity. But perhaps the most telling clue came from rotational data. Using time series photometry, astronomers measured subtle variations in the brightness of 3I Atlas across several days. These changes were consistent with a slowly rotating nucleus, with a likely period between 11 to 14 hours. Crucially, this rotation rate remained stable throughout the mass loss period. Had fragmentation occurred, even minor cracking, the rotational period would have changed. Uneven outgassing from a newly exposed face would create torque, altering the spin, but no such change was detected. The spin axis remained aligned and the coma maintained symmetry. So how is it possible to lose 13% of your mass without breaking? The answer may lie in the composition and internal structure of the comet. 3I Atlas appears to be composed of low-density, highly porous material, with internal pockets of volatile ices surrounded by a matrix of compacted dust and fine silicates. Instead of pressurized gas building to the point of explosion, heat may have diffused inward slowly, allowing volatiles to sublimate and escape through existing channels or vents. This process is known as subsurface migration, where gas molecules move laterally through porous material before escaping at the surface. It leads to gradual erosion, like a glacier melting from below, rather than a surface implosion. This would explain both the consistent mass loss and the absence of fragmentation. Additionally, the comet's likely origin in another stellar system may have shaped it differently. It could have formed in a low-temperature, low-pressure environment, giving it a more resilient crust, or a layered architecture that acts as insulation. Such features would allow it to vent gas without collapsing. Whatever the mechanism, 3I Atlas has shown that interstellar comets may behave very differently from local ones. Whereas solar system comets often crack, tumble, or dissolve, this one endured a 13% reduction in mass, equivalent to millions of tons of ice and gas, with quiet grace. No explosion, no debris field, just slow erosion. A whisper of loss, not a scream, and that quiet durability may be the most alien thing about it. At first glance, the term anti-tail might sound like science fiction. In truth, it's a very real and very rare cometary phenomenon. Unlike a normal comet tail, which streams away from the sun due to solar radiation pressure and solar wind, an anti-tail appears to stretch toward the sun, defying expectation and visual logic. In the case of 3I Atlas, the anti-tail didn't just appear, it dominated the visual profile, and that has created a serious scientific puzzle. The earliest signs of the anomaly emerged in late October 2025, just before the comet's perihelion. Astronomers using long-exposure imaging from telescopes in Chile and Australia began to notice something strange, a faint, narrow feature pointing in the wrong direction. At first, it was assumed to be an image artifact, but the signal persisted across multiple instruments and conditions. By October the 28th, both the Very Large Telescope, VLT, and the Pan-STARRS survey in Hawaii had independently verified a structure extending toward the Sun with a measurable angular length of approximately 0.4 degrees, equivalent to nearly 500,000 kilometers at 3I Atlas's distance from Earth. This was not a trick of light or a photographic illusion. It was real. But how could it exist? Under standard comet physics, dust particles released by the comet are pushed away from the Sun by radiation pressure. These particles form the classic dust tail, which curves gently due to the influence of the comet's orbital motion. Gas molecules, ionized by solar ultraviolet radiation, are swept even more rapidly outward, creating the plasma tail. There's no known physical process that causes cometary material to stream toward the Sun, except sometimes there is. An anti-tail forms when the geometry between Earth, the comet, and the Sun is just right. If the Earth passes through the plane of the comet's orbit, and if the comet is releasing large, slow-moving dust grains, those particles can appear to trail in the direction opposite the dust tail, creating the illusion of a sun-pointing feature. It's not actually moving toward the Sun, it's a perspective effect, where the dust lies along the orbital plane and reflects sunlight back toward Earth. But here's the issue with 3I Atlas. The orbital geometry doesn't fully support this explanation. During the period when the anti-tail appeared brightest, October the 28th to November 2nd, the Earth had not yet passed through the orbital plane of 3I Atlas. That crossing wouldn't occur until mid-November, by which time the anti-tail had already begun to fade. The angle was close, yes, but not close enough to create such a prominent forward-facing feature under normal conditions. Moreover, modelling of the dust dynamics revealed another red flag. The particles required to form such a structure would need to be large, slow, and long-lived, yet none of the expected infrared signatures for such grains were detected by JLAB-STI or NEOWISE. There was no corresponding thermal signature, no sign of silicate reflection, no dense inner dust region to explain the anti-tail's brightness. This left astronomers with two troubling possibilities. The anti-tail was made of non-silicate material, perhaps exotic organics or carbonaceous compounds that reflected but did not radiate in the IR, suggesting an unusual composition. The anti-tail was not formed by dust at all, but by a directional gas release or even a magnetically influenced structure, something never conclusively observed in a comet before. Either explanation would challenge existing models. Some theorize that 3I Atlas might be venting material through narrow jets, triggered by rotational dynamics or internal layering. If those jets were consistently aimed sunward, perhaps due to axial alignment, They could create a visible plume that mimicked an anti-tail. Others speculated on plasma interaction with the solar wind, though no coherent, magnetic field structure has yet been detected. What makes the anti-tail even more fascinating is its timing. It coincided with the peak hydroxyl absorption event, suggesting a possible link between chemical outgassing and this optical oddity. In the end, the anti-tail of 3I Atlas is not just an atmospheric quirk, it's a message wrapped in geometry and mystery. An interstellar visitor doing something we've only rarely seen, in a way we've never fully explained. When the MeerKAT radio array detected a faint but coherent absorption signal from 3I Atlas on October 24, 2025, the astronomy community was both thrilled and cautious. The signal came in at 1665 and 1667 MHz, known hydroxyl, OH, transition frequencies. But it wasn't an emission, it was absorption, a dip, a void, and that, paradoxically, is what made it fascinating. In radio astronomy, absorption lines typically occur when a cloud of gas, often cold, diffuse and backlit by a bright background source, absorbs specific frequencies of radio energy. These missing frequencies appear as dips in the spectrum. They're valuable for identifying molecules, measuring velocities and estimating gas densities. But in this case, something was off. There was no background quasar, no known galactic radio source behind 3I Atlas at the time of the signal. The absorption occurred in what should have been radio silence, a dark region of sky where nothing should be transmitting. And yet, two coherent lines appeared, simultaneously, briefly, and with precision matching molecular OH. That opened the door to a wild but increasingly discussed hypothesis. Could absorption itself be used as a communication medium? This concept is unconventional, but not without precedent in theory. In some speculative branches of astrophysics and SETI, search for extraterrestrial intelligence, researchers have considered the possibility of using controlled absorption, not emission, as a way to encode information. Think of it like sculpting silence. Instead of broadcasting a signal, a sender could manipulate the timing, spacing, or frequency profile of what they block, selectively removing certain frequencies in a predictable pattern. To a sophisticated receiver, the absence becomes the message. It's not about what you send, it's about what you erase. In the case of 3I Atlas, the idea seems absurd at first. After all, we're talking about a comet, or at least what appears to be one. No engines, no radio antennae, no propulsion. But then again, this isn't an ordinary comet, it's an interstellar object with an unusually tight orbital alignment with planetary geometry, a sudden sharp appearance of hydroxyl absorption, not emission. No tail, but a structured, short-lived anti-tail, a mass loss rate that mimics active regulation, and a signal that emerged only once, right before perihelion. If one wanted to camouflage a message, hide it beneath plausible chemistry, using natural, molecular transitions would be a brilliant strategy. Hydroxyl lines are expected in comets. But a precise coherent dip without a known background source, that stands out. Some have proposed that an advanced civilization could seed an object with specific molecules, like OH radicals, and time their release and absorption to match moments of optimal visibility from inhabited planets. The result? A signature that looks almost natural, but deviates just enough to raise questions. A form of chemical steganography, hidden in plain sight. Skeptics argue, rightfully, that there's no evidence the signal was modulated or encoded in any meaningful way. No pattern was detected, no pulse train, no shift between polarizations, and it's likely the signal was nothing more than a brief interaction between cometary gases and ambient radio noise from distant stars or even Earth-based leakage. Still, the coincidence of timing, the uniqueness of the signal, and the chemical plausibility of hydroxyl as an engineered absorber have left the door open. Absorption, after all, is how we study the universe's earliest light. We read it in the gaps, the fingerprints of hydrogen clouds on ancient starlight. What if someone, or something, has learned to speak through those same gaps? A signal not sent but subtracted, a message written in absence, not presence, a voice that only appears when it goes silent. Whether 3I Atlas meant to speak, we may never know. But for one moment it seemed to say something by taking something away. In the wake of the hydroxyl absorption signal detected from 3I Atlas on October 24, 2025, the internet lit up with speculation. Forums, X threads, and fringe YouTube channels rushed to interpret the significance of the signal. Some claimed it was just water vapour. Others went further, much further. Within hours, a claim began to circulate that the absorption signal matched the Fibonacci sequence. The theory went like this. If you analyse the dips in signal strength, the depth and duration of the twin absorption lines at 1665 and 1667 MHz, and plotted their curve, the resulting waveform resembled a golden spiral. From there, some speculated that the object was broadcasting a mathematical pattern, one that points to intelligence. The Fibonacci sequence, after all, appears in nature, art, DNA, and galaxies, a cosmic fingerprint of order. But the claim was false. Worse, it was deliberately manipulated. By October 25th, amateur analysts began sharing screenshots of spectral graphs, supposedly showing a Fibonacci-derived structure. They claimed that the spacing between microdips in the spectrum followed the ratio 1.618, the golden ratio, and therefore proved that the signal wasn't natural. Some even overlaid spirals on blurred telescope images of the comet, asserting visual confirmation. But none of these images came from real observatory data. They were composites, often generated using public domain, images of other comets, edited with filters to create the illusion of mathematical harmony. The spectrograms were doctored, with noise patterns artificially arranged to mimic a Fibonacci spiral when viewed at low resolution. NASA and the South African Radio Astronomy Observatory, SARAO, quickly debunked the claim. The actual raw data from MeerKAT, when published, showed clean, narrowband absorption lines with no such structure. There were no micro-dips, no golden spiral, no Fibonacci pattern. Still, the idea refused to die. Why? Because it fit the narrative that many wanted to believe. A beautiful mathematical sequence hidden in a cosmic signal. It's the ultimate science fiction fantasy. It suggests purpose, design, meaning. For those seeking signs of intelligent life, the Fibonacci claim was irresistible. But there's a deeper reason why this hoax gained traction. It mirrored past events in astronomy. In 1977, when the famous WOW signal was detected by Ohio State's Big Ear telescope, its origin remained a mystery. It lasted just 72 seconds and was never repeated. In the decades since, it has become the subject of endless speculation, with numerologists and fringe theorists projecting patterns into the data. Fibonacci spirals, prime numbers, musical ratios. The same psychological pattern played out again with 3i Atlas. The human brain is wired to find order in noise, to extract patterns from randomness, especially when we want to believe. It's called apophenia, the tendency to perceive meaningful connections where none exist. And yet, the false Fibonacci claim has had an unintended benefit. It forced professional astronomers to reaffirm the value of data transparency. Within days of the hoax spreading, SARAO released high-resolution spectral data from the MeerKAT array. NASA responded by publishing time-tagged comet tracking logs. Citizen scientists were invited to inspect, replicate, and challenge the findings. This rapid openness helped restore public trust and brought more eyes onto real evidence, rather than conspiracies. In the end, the Fibonacci spiral wasn't there, but something else was. A coherent signal, a real chemical fingerprint, a message not from mathematics, but from molecular physics. 3i Atlas didn't speak in golden spirals. It whispered in hydroxyl, and then moved on. The hoax faded, but the comet remained. Not a bearer of divine geometry, but of cold, verifiable chemistry. And in that, perhaps, lies a deeper beauty, one that doesn't require myths. Just the silence between two dips in the spectrum, and the truth waiting inside them. The moment the MeerKAT array registered two precise hydroxyl absorption lines on October 24th, 2025, speculation ignited. News outlets raced to report the signal. Social media flooded with theories, ranging from water vapor emissions to intelligent messages hidden in molecular patterns. And as always happens when science brushes against mystery, the public looked to a familiar institution for answers, SETI. The search for extraterrestrial intelligence has long served as both a scientific initiative and a symbolic torchbearer for one of humanity's biggest questions. Are we alone? So when the 3i Atlas event unfolded, the SETI Institute in California was immediately thrust into the spotlight. Their initial reaction was cautious. Within 24 hours of the MeerKAT detection, SETI issued a statement. It confirmed that their team had received the raw radio data and was conducting independent analysis using their own instrument arrays, particularly the Allen Telescope Array, ATA, in Northern California, which was already tracking interstellar objects on a limited schedule. The statement was clear. At this time, the observed absorption is consistent with natural hydroxyl behavior in cometary activity. However, due to the object's interstellar origin, further monitoring is warranted. But that careful language only fueled more confusion. To the general public, monitoring is warranted sounded like a cryptic nod toward possible alien activity. Reddit threads misinterpreted the statement as a veiled admission. YouTube personalities released urgent videos with titles like "SETI knows something they're not telling us," and "Why are they so quiet about 3i Atlas?" In truth, SETI was doing exactly what scientists are trained to do: wait, test, replicate. But the gap between scientific rigor and public expectation had never felt wider. As SETI began its own observations, several facts became clear. ATA did not detect any additional absorption or emission lines from 3i Atlas, though it admitted that atmospheric conditions and scheduling conflicts limited coverage. SETI's data team published a preliminary report stating that the original hydroxyl absorption lines were not repeated in subsequent passes. They also emphasized that absorption is not the same as broadcast. The signal was a passive phenomenon, not an active transmission. But for many in the public sphere, this wasn't enough. Online, a narrative began to form that SETI was either hiding the truth or afraid to admit the implications. People pointed to the unusual trajectory of 3i Atlas, its lack of visible tail, and the timing of the signal, claiming that the Institute was being overly conservative. SETI responded again, this time through a live-streamed panel on November the 1st, featuring astronomers, chemists, and astrobiologists. The message was direct. There is no evidence that this was a message from an intelligent civilization, but we are not dismissing anomalies. That's what science is supposed to investigate. They used the opportunity to explain how cometary chemistry works, what hydroxyl is, and how absorption features can appear without any artificial cause. They even brought up similar events from past comets, including 2I Borisov, which showed volatile outgassing in unpredictable patterns. Still, the public divide remained. The issue wasn't just science, it was expectation. People were hungry for contact, for wonder, and 3 Atlas had delivered just enough weirdness to ignite that hunger. SETI, bound by the guardrails of evidence, couldn't feed the fire. It could only hold the lantern steady. But even within SETI, quiet curiosity persisted. The organization allocated extended monitoring time to track other interstellar objects passing through similar coordinates. Some researchers privately admitted that 3i Atlas was the most intriguing interstellar case since Oumuamua. In the end, SETI did what it was built to do. It listened, it tested, it told the truth. But the public wanted more than truth. They wanted contact, and when they didn't get it, they filled the silence with imagination. Every once in a while, science stumbles across something that quietly shakes the foundation of what we think we know. The interstellar visitor known as 3i Atlas didn't crash into Earth or beam out a decipherable message. It didn't light the sky with fire or leave behind a metal artifact. But what it did reveal, in subtle chemistry, silent geometry, and evaporating vapor, may be even more profound. Because if the data holds up, 3i Atlas has done something no interstellar object has done before. It interacted with our planet's line of sight in a way that seemed timed, structured, and molecularly complex. Not artificial necessarily, but intelligently rich in the language of chemistry. And that raises the question, what does this mean for life in the universe? To answer that, we first have to step back from the romanticized version of life, intelligent, technological, and communicative, and instead explore the quiet, slow, biological scaffolding that supports all living systems. The hydroxyl OH absorption signal observed on October 24, 2025 is a familiar one. Hydroxyl radicals are common in comets, usually formed by the breakdown of water, H2O, under solar radiation. But what makes the 3i Atlas signal unique is not just that OH was detected, it's how clean, localized, and non-random the absorption was. It appeared once, briefly, and without a known background source, suggesting an intentional window of detectability. Now, hydroxyl is more than just comet exhaust. It's one of the fundamental reactive species in organic chemistry. It plays a central role in breaking down methane and formaldehyde in planetary atmospheres, catalyzing reactions in prebiotic chemical networks, forming hydrogen bonds in aqueous environments, the kind we associate with early Earth conditions. So, when an object from another star system releases well-timed molecular patterns of hydroxyl, carbon monoxide, methanol, and possible organic residues like PAHs, polycyclic aromatic hydrocarbons, we're not just seeing a chemical process, we're seeing a bridge between astrochemistry and biochemistry. This supports a growing body of evidence that life's building blocks are not unique to Earth. In fact, they may be common byproducts of interstellar processes, forming in cold molecular clouds, aggregating in icy grains, and being carried across light years on rocky wanderers like 3I Atlas. We've already detected glycine, the simplest amino acid, in cometary material. We've found organic-rich meteorites that landed on Earth. The European Rosetta mission even confirmed that Comet 67P carried both oxygen and amino acid precursors. Now, with 3I Atlas, we're seeing the same patterns emerge from an object that never belonged to our solar system. This strengthens the argument that the ingredients for life are not local, they are universal. If that's true, then we must consider the implications. Planetary systems everywhere may be seeded with prebiotic chemistry from inbound interstellar debris. Life may not begin through rare miracles, but through repeated chemistry-driven events. Intelligent life, though rare, may arise in more places than we dare believe, simply because the molecular groundwork is laid everywhere. The 3I Atlas encounter also challenges our assumptions about how life might communicate, perhaps not with language or light, but with chemical signatures, timed to intercept us not with a message, but with evidence of shared ancestry. Maybe, in the grand conversation of the cosmos, life doesn't always speak. Maybe sometimes it just releases a breath and waits to be noticed. And if 3I Atlas was that breath, then we may have just inhaled a fragment of a distant beginning. Not proof of alien life, but a quiet affirmation that life is not a miracle of Earth, but a consequence of the universe itself. When scientists study the cosmos, they are trained to search for signals, not stories. They look for repeatable data, measurable forces and predictable patterns. But every now and then, an object like 3I Atlas drifts into view, and suddenly, data begins to resemble narrative. Not because the universe is writing one, but because we, as observers, are finally ready to listen. And so, as 3I Atlas continued its silent arc past Earth and away from the inner solar system, many began to ask, was there a message? The answer depends on how we define a message. If we expect an intentional radio transmission, a sequence of prime numbers, or a universal mathematical code, no, 3I Atlas did not deliver that. There was no explicit greeting, no alien broadcast, no language we could decode. The hydroxyl absorption lines detected on October 24th were brief, natural, and chemically consistent with cometary activity. But sometimes a message doesn't come in words. Sometimes it comes in structure, timing, and presence. Here was an object, travelling for millions of years through interstellar space, composed of complex molecules associated with life's precursors, arriving on a trajectory aligned with Earth, Venus, and Mercury, emitting no visible tail, but releasing material in a way that defied local comet behaviour, losing 13% of its mass without fragmenting, displaying a rare anti-tail and timed absorption event during a brief geometrical window. None of this proves intent. But the pattern, the stacking of anomalies, invites us to reconsider what a message even is. Perhaps the real message isn't that someone is speaking to us. Perhaps the message is that the universe knows how to make things that resemble speech, without ever saying a word. It's easy to dismiss this as anthropomorphism. After all, comets don't have consciousness. They don't plan trajectories or decide when to release gas. But when a chemical event times itself so precisely that it appears detectable only from Earth's position, we are forced to entertain at least one of two possibilities. It is a natural coincidence so statistically strange that it commands investigation. It is a signal of processes we don't yet understand, not artificial, but beyond our current models of interstellar chemistry and physics. In either case, it means this: the cosmos is more responsive to our gaze than we previously believed. The real message of 3i Atlas may not be encrypted in a transmission. It may not be something we were meant to receive. But by showing up when it did, how it did, and behaving in a way that stretched, but didn't break, scientific models, it did what all good messages do. It forced us to reconsider our assumptions. That's the core of science. Not to find all the answers, but to ask better questions. Questions like, why do interstellar comets exhibit such variable chemistry? How common is water in objects beyond our solar system? Could orbital geometry play a role in visibility for life-bearing planets? Can molecular absorption, not emission, act as an intentional carrier of information? These are not the kinds of questions we were asking 10 years ago. We're asking them now because of 3i Atlas. In the end, maybe the real message wasn't hello. Maybe it was something quieter, more profound. Maybe it was, you're not alone. Not because we are here, but because you are now capable of looking, noticing, and wondering. And maybe that's all the universe has ever wanted us to do. To wonder, to observe, and to pay attention when something strange passes through the dark, even if it never speaks again.